Hey everyone, thanks for coming out. Our talk today is how Spotify evolved its ML platform to power generative AI use cases, and we can start. So quickly, some introductions. My name is Grace, and along with my colleague Abdullah, we're both engineers on one of Spotify's machine learning platform teams. Our agenda today will be pretty straightforward. I'll cover an overview of HRX, which is Spotify's ML platform. I'll go into the platform changes we've made under the hood, so to speak, in the last year. Then Abdullah will tell us about how we've made user-facing changes so we can take advantage of those infrastructure improvements. So HRX, Spotify's ML platform, began with its first iteration in 2018. It was originally built on top of Kubeflow and GCP to support TensorFlow use cases and an opinionated path to production. But by 2022, there was a large gap in serving data scientists and researchers who didn't use TensorFlow or wanted other frameworks. So we built a 2.0 platform called HRX, which leverages managed rate infra on top of Google Kubernetes Engine, also in GCP. A few things to know is that it's centrally managed multi-tenant infrastructure, so many teams use our platform at the same time. They primarily interact with our platform via a Python SDK and CLI that we manage. And otherwise, for platform and business logic, it's mostly a couple Golang-based services and deployments behind the scenes. Just to illustrate how much HRX has grown in the last year since the previous Ray Summit, we've grown from 80 teams using HRX at Spotify to about 120. We've gone from 100 Ray clusters a week to 1,400. It's about a 10x increase. And we've increased our Kubernetes footprint from one cluster with 500 nodes to 3 clusters with around 4,500 nodes. So it's a lot of growth, and we want to highlight a couple themes throughout this talk about how we've adapted our platform to meet those needs. Number one has been reducing friction through standardized development practices. We have a lot of knobs and levers our customers like to make use of with their Ray clusters, and we want to give them an intuitive way to do so. Secondly, you'll hear how we provided sufficient resource capabilities, i.e. sheer node capacity, to meet those volume increases. Thirdly, accommodating Gen AI on a multi-tenant cluster. So not just enough resources, but fair sharing of resources. And finally, we'll touch on a few platform and reliability improvements we've made with observability and redundancy as well. So here's a succinct diagram of HRX architecture. Obviously, there's a whole ML ops ecosystem around this that's not being shown. Like we use MLflow at Spotify and a couple of different storage flavors in Google Cloud. But for the compute part, this is really succinct. It's a user who interacts with our Python CLI or SDK. And from there on, they submit a Kubernetes custom resource request for a Ray cluster that goes to our platform-managed webhook. More on that in a bit. But from there on, the webhook passes the Ray cluster request to KubeRay, which we simply deploy from upstream. And that builds or creates and manages the Ray clusters from there on. So that was 1 year ago, and now we're in a multi-cluster universe, and I think it's worth talking about the evolution and how we did it and why we did it. Why did we do it? We were running out of node IPs to provision our Ray clusters upon. With the adoption at Spotify, we were running out of IPs in our subnets to provision Ray clusters with the Kubernetes autoscaler. And when this happens, you get Ray clusters that hang indefinitely in your terminal, or you get a weird deadline exceeded error, and it's not a good experience. So we made the choice to provision a second 4,000 node cluster. I think will be good for a while. And we managed to do that quite easily from our side because we manage everything declaratively with Terraform. So it's just a matter of rinsing and repeating a couple of resources in Terraform and updating the config we cared about. From the user side, our multi-cluster experience has made a lot of headway because we've chosen for now to use our SDK as the de facto gateway between the two Kubernetes clusters. Simply put, if I'm at my terminal and I want a Ray cluster to muck around with some Jupyter notebooks, we default to the original Kubernetes cluster. If I want to submit a Ray job, we default and send you to the larger sort of batch production Kubernetes cluster, if you like. Finally, we've instantiated a test cluster because we have made a lot of changes to the platform. We're always doing node upgrades, QRay operator upgrades. We're testing our custom webhook. So this test cluster is very, very useful for validating those changes before we roll them out to users and could potentially cause an outage. So it's great that we have enough nodes, but that's not necessarily an optimization. I want to talk a little bit about how we've improved the network bandwidth layer with our platform. So the problem is that when you have a Kubernetes cluster with hundreds or thousands of nodes, you have RAID clusters represented here by these blue circles that are spanning many, many nodes. They incur slower network bandwidths because the data simply has to travel further, and that's not a good experience when you're doing distributed training, checkpointing, or the like. So we worked with our Google support team to implement a couple best practices I'll highlight here. We did all this with Terraform in just a few lines, and it includes compact placement, so putting the nodes closer together in physical space, Google Virtual NIC for improved I/O on our virtual machines, and Nickel Fast Socket, which is an extra optimization layer on top of some of NVIDIA's common low-level libraries. I want to move now from like the bare metal, if you will, of the platform to some of the platform and business logic we've worked on. As a platform, we have to maintain a couple pieces of logic that are specific to our platform. What do I mean by that? Sometimes, or often, it's usually the case where we are putting RAID clusters on distinct node pools in our Kubernetes clusters, or maybe we're restricting a specific kind of hardware accelerator to certain namespaces. So up until this year, all of that logic lived in our client-side Python SDK. It's easy enough to develop in, but the problem is it's difficult for our users to constantly be upgrading, especially if they encounter a transient dependency, like a pip package changed or something else that ruined their day. It doesn't always make sense for them to take on that toil for us. So we made the decision to migrate this logic to our own Kubernetes webhook. We were able to do this pretty easily. We leveraged QBuilder, which made a lot of the scaffolding for us, and we just put our logic into the relevant parts of the webhook. You can see here in this example, the webhook merely takes the incoming RAID cluster request with this YAML on the left. It's minimally formed. It takes that YAML and injects the annotations that we care about, and it sends it on its way to the kubearray operator as normal. This is really good because now our platformers can develop all the logic that they like and release it without the customers even having to know that we've upgraded our backend. One more note when it comes to the platform logic that we've improved in the last year. Let's say that I've provisioned 4 GPUs and my RAID cluster starts spinning up, but I can only get 2 GPUs because the rest are allocated somewhere else. Well, now I'm holding on to 2 GPUs without using them, and I'm squandering those resources, being cost inefficient, what have you. We decided that some of these problems with GPU and resource sharing started to look like queue problems. So enter this very aptly named project called Q with a K. We use it to basically instantiate a queue in front of our batch workload cluster. And when folks go to submit their jobs to the cluster, they go to a local queue for their namespace, and then that all gets merged into a global cluster queue, which then does gang resource scheduling. The really nice thing about gang resource scheduling is all or nothing. So instead of waiting with a halfway provisioned RAID cluster, my job is ready once all 4 GPUs are ready, and I can just go on about with my day. It works really well for us because it's a natural solution to this problem, and also it has a really great integration with the RAID job custom resource. All we have to do after we install it on our cluster is add a few annotations to our RAID job CR, and we're up and running. It's a bit of an implementation detail, but worth mentioning if you use Google, that we use Google's dynamic workload scheduling to take care of the actual provisioning of the GPUs themselves. Here's a bit of Q and QDWS in action. As you can see, we have a namespace, or a couple different namespaces, one per team typically. The job goes through a workload which loads itself onto the local queue. And those local queues all feed into the global cluster queue on our Kubernetes cluster. And once your job is ready to go, the RAID job's provisioned, and you can interact with it as normal via our SDK or CLI. So one more thing I want to mention in terms of the user experience and how we've made all these changes to our platform. We try to keep the user experience in mind as we roll out all these different changes. And something to make note of is 3 SLOs we've implemented this past year. One is the percentage of Kubernetes clusters that are available for array cluster workloads. As we mentioned, when we run out of nodes on our Kubernetes cluster, we no longer can provision array clusters, so we definitely want to keep an eye on that. That's a part of what this diagram is showing. When we hit our plateau, the outage begins, in effect. Secondly, we monitor the percentage of array clusters in a ready state for a given window of time. If suddenly 80% of our array clusters or less are not ready, we know we've regressed in some way. And finally, and this is upcoming for us, we are planning to operationalize the time it takes for an array cluster to become ready in the first place. A couple of our engineers made this contribution earlier this year to KubeArray, and we plan to track this metric so we can monitor if it suddenly is taking 10 minutes for an array cluster to become ready. So this all helps us make sure that we can roll out these improvements without actually worsening the experience for our users inadvertently. With that being said, I'll hand it over to Abdullah, and he'll take you through our user-facing changes.
Thank you, Grace. So for the first half, Grace talked about the improvements we made at the infrastructure level that were absolutely essential to enable the use cases that we saw emerging through GenAI. The second half, we will be talking about how we take those improvements and provide it to our users. And I would just like to emphasize on one thing. So yesterday at the keynote, Robert mentioned about that complexity is the enemy in this era. We saw that live on our platform. A lot of tools that we introduced, our effort on the user side was to lower the complexity and meet users where they are in their ML journey. So a power user could interact with our platform at a low level, but we should allow or enable our users to not think too much about the infrastructure level concerns and spend most of the time on the actual workflow that they're building. So the second half, we will talk about this little piece at the center, which is our interfaces that we provide to our users to interact with our infrastructure. So we will talk about some features. Here we show you just a typical GenAI dev lifecycle that we were able to identify based on the user journeys we saw. The ones highlighted in green are the ones that we will be talking, or the features that we will talk about correspond to these bubbles. So it's OK if you don't pay too much attention to it, because we will be coming back to it with each feature that we mention. So just to kick off, how does a user who is just getting started with Hendrix, how do they interact with our platform? What's the first entry point? Spotify built a tool called Backstage, which is also open source right now, so which means any one of you interested in it can take a look at it, use it. It's a software catalog. What we do internally is we provide a component, which we call Hendrix ML component, and the motivation really is to bring all the golden practices, or a golden path, if you may, in one place. So if you're a user, you create a component on Backstage, and with it, you get a software development kit, you get the libraries that are essential to interact with Hendrix, you get the infrastructure that is needed to run your workflow, both during the prototyping stage as well as the production stage. So it really is our effort to consolidate the fragmented space that we operate in. And so moving on, before we talk about the features, we would like to mention this layer that we built, which we call Hendrix config layer. Again, like I mentioned, complexity is the enemy. Our goal through this layer was to provide users useful abstractions that they can interact with when it comes to creating an array cluster, submitting a job. So how does a config layer work with Hendrix? A user simply, so we provide, like I said, abstractions that users can maintain in their YAML files. Hendrix config layer, what it does is it loads those YAML files, does the validation, and produces a complete and valid low-level custom resource that could be array cluster, that could be array job, and then applies it to our GKE or Kubernetes infrastructure. So the first concept that we tried abstracting is array cluster. And the template that we'll follow for the following slides as well is, on the left, you can see what a user has to maintain, which is their YAML file, which is our abstraction over array cluster custom resource. Top right is just a snippet to show that our SDK, which is Hendrix config layer, sits in between, does the validation, and applies the manifest that is then produced that you can see at the bottom right. So Ray cluster is one abstraction that we provide, using which users can create a Ray cluster on our managed infrastructure. The second abstraction that we provide is Ray job, which is, again, people familiar with KubeRay and its custom resources. Ray job is another custom resource. Similar pattern on the left side, you can see a YAML file that a user has to maintain, not as low level as the actual Ray job CR. The SDK then does validation and produces a complete and valid custom resource that could then be applied to our managed infrastructure. It would then create a Ray job, which, again, Ray job creates a Ray cluster, runs a job on it, and then deletes the Ray cluster. So now, well, having talked about those two abstractions that we provide, and we do provide other as well, but those two were critical to understand the features we'll be talking about. With that, we can now get into the actual features that we were requested to build as Spotify recently through GenAI use cases, and how we went about it. The first one was actually motivated by a lot of teams who wanted to create a Ray cluster that can handle heterogeneous workloads. So imagine, a single workload that has different stages with different resource requirements, some performing a CPU-intensive data processing, while another stage in that workload performing a GPU-intensive training. So initially, when Hendrik started, we only allowed one worker group in a Ray cluster. And seeing this problem or this feature request from our users, we moved towards providing them the ability to create multiple worker groups. Again, we tried lowering the complexity. How it looks like is top left, a YAML file that I showed you for Ray cluster. They simply need to make some adjustments to that YAML file. And our config layer would handle the validation and would handle actually populating a valid Ray cluster custom resource that can then create a Ray cluster with multiple worker groups, each with its own set of resource requirements. And I hope the diagram helps. We tried color coding to make the point more obvious. Secondly, similar idea, there was a distinct use case at Spotify where a team wanted to host a VLLM on a Ray cluster. And so what they really wanted to do was create a Ray cluster where you have a worker group dedicated to a VLLM deployment. And so the problem really there was, how do you make sure that that deployment has dedicated resources for it, and other processes are not interrupting or are not claiming the resources on that worker group? And so what we did, the feature we enabled was the ability to create a separate worker group, which we call Sidecar worker group. Again, the user journey seems very similar. The user YAML file, they have to specify a Sidecar worker with, so what happens in a Sidecar container, I should actually briefly explain. The main container does not have most of the resources, and there's a Sidecar container where VLLM is deployed that actually gets allocated the resources that the user requests. That way we can ensure to some degree resource isolation, and that no other process is claiming those resources. What a user has to do is, again, a YAML file, adjust it a little bit according to our guidelines, the schema that we provide. Our SDK layer, our config layer, would then, again, do the validation, make sure it's valid, produce a custom resource that can actually implement those changes, and then submit it to our cluster where KubeRay would then create a Ray cluster with a Sidecar worker group. Another solution that another problem that we saw was more on the storage optimization. So the problem here is really just one example is large-scale distributed training jobs often require some storage capability to ensure reliability. So imagine there's a workload, which is a long-running workload, or Ray cluster that is, that requires to live for a long period of time, and you've already done some fine-tuning on it. For some reason, it could happen that the Ray cluster goes down. So to ensure that the work that you've already done, so GPU that you've utilized in that workload, doesn't go to waste, we saw a feature request where users wanted some storage capability for their long-running jobs. We had another solution, but then recently we moved towards GCS Fuse, Google Cloud Storage Fuse, which essentially what it does is it allows you to treat a Google Cloud Storage bucket as local file system. So we've seen a lot of teams at Spotify who use it for distributed model checkpointing. There's also some teams who use it for other data that they need for a long-running job. But this has really made our life easy. And again, if as a user you want to use it, we tried lowering the complexity. So you can see the changes are just required on the YAML level, what bucket you want to use. The SDK then does the validation, produce a Ray cluster custom resource that can attach a Google Cloud Storage bucket as local file system with it. The diagram tries to help you visualize how it looks like. There's a Ray cluster where head and worker nodes have access to this single bucket or this GCS bucket and can work with it like it's a local file system. So Grace already talked briefly about, or talked about QDWS on the infrastructure side, things that we had to implement or how we had to move towards QDWS. And the problem is, I hope is visible, but just to reiterate on the problem, it is that we needed gang scheduling for expensive, limited hardware accelerators like GPUs, where you have a lot more teams fighting for resources, and you need to ensure that the resources are not underutilized, not over-provisioned, and each team gets its fair share of usage. Now, there's a lot of complexity, as you saw earlier, a lot of stuff that we had to implement under the hood to enable QDWS, but do we expose our users to it? Of course not. We try to lower the complexity and just allow them to, with a single config change, as you can see, top left panel, if they do want to use queued provisioning, they enable that option in the config file, use our interface, and our config layer would then would validate and produce a valid Ray job custom resource, the abstraction that I talked about earlier. So there's Ray cluster abstraction and Ray job abstraction. And by simply providing this one example, this one config option, they could opt in and use queue provisioning, which means the Ray job that they create would be queued, and as soon as the resources required by it could be provisioned, that's when queue would admit it, and DWS would work on GPU obtainability. So that's how it looks like on the user side. Again, just a config change, and they don't have to worry too much about the underlying resources like local queue, global queue, and other stuff that is needed to set it up. And finally, to connect all the dots, so most of the features that we talked about could be used, are used during the prototyping or ad hoc stages. But at the same time, we do realize that our users need to, once they're happy, so if you talk about that diagram that I showed you earlier, where different stages in a Gen AI dev lifecycle, let's say they keep iterating on some configuration, on some solution that they have, eventually they would want to deploy it, or they would want to run a production job and move out of the prototyping stage and actually have a more robust scheduling. So we need to make sure that whatever solution we have for production, for scheduling, it could leverage all the features that we talked about, all the infrastructure improvements, all the user-side features, all the config changes that we listed. For our scheduling, we use Flight, which is a workflow orchestrator. We used to be on Luigi. Now things are moving to Flight. Our key challenge on that side was our organizational design, which is usually data workflows in Spotify. They run on a different GKE cluster, which for simplicity, we can call it data GKE cluster. And within that workflow could be a task that needs to run as a Ray job, which means it needs to create a Ray cluster and run a job on it, delete the cluster. But that Ray cluster needs to be created on the ML GKE cluster. So we have two GKE clusters, data GKE cluster, ML GKE cluster. The problem really was how do you align this organizational design, and how do you enable a task in a different, or a pod task in a different GKE cluster to create a Ray cluster, run a Ray job on a different GKE cluster. Quickly, for that, what we did, we have our internal plugin. There is an open source solution. We did some investigation. At that time, our internal solution was more appropriate. But what our internal plugin does is that it does exactly what we described earlier, creates a Ray job manifest, optionally use queued provisioning, and then run a job on ML GKE cluster. You can see there's a quick example of how it looks, or how the workflow looks like in Flight. So this example shows two tasks. There's one regular task, which would run on the data GKE cluster because it doesn't require any Ray infrastructure. But if you have a task that needs to run as a Ray job, all you need to do is you need to initialize a Ray job config and then decorate that task with that config. What would happen on the Flight side is Flight has its own operator. It would look at the config, look at the task, create a Ray cluster, run that task on that Ray cluster, and then delete that Ray cluster once the task has executed. So that was really just some of the user-side changes that we made. But I would like to emphasize again, through all the features, there's a common on the user side. There's a common theme, which is that we need to bring the complexity down and really just enable the user to move at a better velocity. And with that, I would call Grace back up on the stage to wrap things up.
Cool. Thanks, Abdullah. Yeah, just to wrap up quickly, wanted to highlight some of the takeaways we hope that you have from this talk. Firstly, to design an interface expressive for users and extensible for maintainers. As Abdullah demonstrated, there are so many features we gave to our users with the SDK, and we managed to do this in an extensible way using our cluster and Ray job configs. Secondly, ML platforms require optimization throughout the stack, but be strategic about the complexity of your optimizations. We had network optimizations, resource and storage optimizations, but choose a solution that makes sense for you and what you need. And lastly, maintainability and velocity don't have to be trade-offs. We strongly believe having those SLOs, the test cluster, and working directly with our users helped us deliver a lot of these changes while keeping the user experience seamless throughout. So with that being said, we'd love to take your questions, and we are hiring, by the way. Feel free to use the mic in the middle aisle if you like.
Hi, the presentation was really good, thank you. I have a question. So when you mentioned the sidecar model and multiple worker group models, do they get deployed in the same cluster, or can they also be deployed across different clusters?
So the question was to elaborate on the sidecar pattern that we talked about and the multiple worker groups. So for multiple worker groups, each worker group gets allocated to a node pool separately. So they could be different node pools. For the sidecar container pattern, there is, when we built that, we called it an experimental feature because that was something that a few teams wanted to use. It wasn't something that we tested and we validated, but it's just one worker group that gets allocated to one node pool. So they could be on different node pools.
Okay, thank you.
Hi, so my question is also about the sidecar worker group. So is that the worker group how the Ray cluster defines worker group? And if yes, how do you make sure those resources are not used by any of the jobs? Because I understand the Ray doesn't provide anti-affinity. Like you can say that this, the resources are preferred and this worker group has these resources, but you cannot say that don't go to that worker group, right?
Yeah, no, so the question is how do we ensure resource isolation for sidecar, for the VLAN deployment on a sidecar container? I guess the solution there was to, if you use a separate sidecar container within a worker group with its own image, and allocate the requested resources to that worker or to that container, not to the main container, but to the sidecar container, then that would provide us some resource isolation where other resources would run on the main container, but won't run on the sidecar container. So by doing that, we hope that that would provide enough isolation for a VLLM deployment.
Thank you.
Thank you.
Hey, I have a question about how you're using DWS and what your cost optimization strategy is for that. Because our team uses it, but we have a hard time understanding how to manage costs related to it.
Yeah, some of the approaches we take to managing costs, we just work directly with our Google support team. We try to take their advice with optimizing costs. A big one for us recently has been logging costs. So we've made the decision to move to making logging optional or at least highly configurable for array clusters with the amount of clusters we procure. That drastically helped reduce our costs, for instance. So, yeah.
Cool. Thanks.
It seems like that was all the questions, but if you do have questions, Grace and I will be here for a while, so please feel free to approach us and ask any question that you have. Thank you.